Okay, hi everyone. I hope you all doing well. In this video, I'm going to show you how to conduct a basic analysis of data and stata, simple descriptive statistics here, so no inference quite yet. And we're going to pick up using a do file that I made that begins with a fairly detailed discussion of why we basically use do files in stata, why we work at this higher level, and why we have some of the kind of standard headers that we do in stata. I'm going to assume that you've watched that video or can watch it if you haven't yet. And I'm going to pick up by simply loading the data, ignoring all the discussion here, and then diving into the analysis. But do go watch that other video if you need to. So we're going to focus in this video on the case of two quantitative variables. And I'm going to select a kind of classic example, which is the relationship between a person's education, denoted R on the GSS and many other surveys, and father's education. So let's go ahead and begin the analysis. So we're going to begin with what's called univariate analysis, or in other words, just examining each variable one at a time. Note that if you're watching this for a project with a class with me, for instance, that does not mean that you should only analyze one variable. It means that you should analyze one variable at a time, but you should do multiple such analyses. So it just means that we're not using techniques quite yet that deliberately try to uncover the association between two variables. So we'll conduct the univariate analysis now. And we can go ahead and start with the respondent's education, and we'll use numeric, and then we'll use graphic methods. So we'll start by pulling out the code book, which isn't always that informative, but for some detailed data sets, such as the GSS, it often is. So we see here that we get the name of the variable label, and we get a type of variable, which isn't directly important to us here. We see that it's numeric. There's other types of variables that you want to be, well, it's really more of a computing technique, actually. So for the most part, this actually can be somewhat misleading in that this is not going to tell you whether this is a quantitative or an interval variable or, interval or ratio variable, I mean to say. So for the most part, you can sort of ignore this, but it is interesting at higher levels. You get the label for the variable as well, which again is not that relevant for quantitative variables. It becomes more important for qualitative. You can see the units here. You can see the range. So we have 21 unique values from 0 years of education to 20, which is also reported here. You can see the missing value codes here. So in this case, we just have one type of missing value, and we'll discuss missing values a little bit later on. In this case, we only have 3 missing values total, which is good news. And it even prints for us some examples. So this is what the data will look like. So pretty helpful. We're off to a good start. Incidentally, if you're poking around for variables and you have a large data set, such as the GSS, where you've got very many variables, and by the way, a way to look at that is to write describe. We're actually going to add the option short here because this is a giant data set. So if I just wrote describe, it's going to give a whole lot of stuff. So let's write describe short. And you can see we get the number of observations, so 2,348 people, and the number of variables, 1,065, which seems to correspond with this very large variable window here. You can also use describe to look at variables too, by the way. And you get this information here, which is helpful. So again, the storage type, the display format, which also is interesting at higher levels, not really that relevant right now. And again, the value label, which is important. You will want to access that for qualitative work later on. And the variable label, which just basically tells you what the people that conducted the survey wanted to call the variable or describe it as, really. And then also this will give you information about what gets printed on certain graphs. So anyways, back to the point I wanted to make before we actually look at the numeric analysis. If you're looking around for variables of your own and you have a giant data set like this, you can do a couple of things. One, you can type in the variable window. So let's say I'm interested in education. I can type in Duke here and you'll see there's a whole lot of things. But be careful though, because it is sensitive to the length of the stem here, basically. So if I type in education all the way, you can see there's actually not that many results. So you may want to try brief stems or stubs here. And you can also pull this up in the command window using the command look for. So look for Duke also pulls all these up here. Okay, so that's kind of hunting for variables and getting some really simple information, but let's actually go ahead and do some real analysis here. So we'll start by tabulating the variable. Tab is actually short for tabulate, not table. Table is a closely related command, but we just need one of them for now. And you can see that this produces a frequency table with frequencies percent and then cumulative percents, basically giving you the cumulative distribution function or the estimate thereof, which gives us a lot of information about the variable. We can kind of see that probably our naive guesses about the distribution. So only 12% more or less of the population had 11 years of education or less in 2018, which seems to track. But then that jumps up to 40% of people had a high school degree or less. And then basically, fairly sizable majority of people had 14 years of education or less, corresponding, roughly to a trade degree or less, which again makes sense. So we get a lot of information here. Now, this wouldn't necessarily be appropriate to do with a basically a less discrete quantitative variable, meaning that the variable can take on more values. So if we tried to, for instance, tabulate age, you would see that this is a little bit harder to look at and make sense of. So be careful using tab with quantitative variables. You really only want to do it if it's a fairly discrete variable. If you have anything that's approaching a truly continuous variable, that is to say one that could take on an uncountable number of values, basically, then this would be potentially disastrous depending on the size of the data set. So be careful there. So in either case, what we would probably want to do instead is go ahead and take summary statistics. So we're going to write sum here, and this oftentimes confuses people because you might think that this means literally to sum up the value of a variable, but actually what this does is produce summary statistics. So we could actually write summarize and we would get the same thing. So let's write that. And I'm adding the detail option, by the way, because it's often most useful. So when we tell Stata to do that, this is the output that we get. So we get some common percentiles, the first, fifth, 10th, or the first decile, the 25th percentile, or Q1, the first quartile, the median, or the 50th percentile, or the second quartile, and then the 75th percentile, or Q3, and so on. We also get the 4 smallest and 4 largest observations, oftentimes not that informative. We get the number of observations. We get the sum of weights, which is a question that we're not going to deal with in this video. We get the mean. We get the standard deviation. We get the variance, which is the square of the standard deviation, of course. And then we get a couple of higher moments about the mean, the skewness, and the kurtosis. We won't deal with these. These basically give more detailed information. They're basically almost like higher powers of the variance in a way. And they're informative in their own right, but we won't deal with them. One thing I do want to note is that skewness is a more complex measure than skew. And so I'll assume for this video that we'll use the simple definition of skew, whereby if the mean exceeds the median, you have a rightward skew. And if the median exceeds the mean, you have a leftward skew. So we'll use the simple definition. So we can see that the mean seems to check out, right? This seems to fit our probably, again, rough guess. The median is 14, again, probably fits roughly our rough guess. Standard deviation, I would be hard pressed to say, but this seems reasonable to me. And we can see that there appears to be a slight, actually in this case, leftward skew because the mean is a little bit less than the median, but hardly by any. So fairly symmetric. At least that would be our basic guess. We'll have to look and see a little bit more later. So let's go ahead and actually do that. And so we're going to go ahead and pull up a graph. We'll pull up a histogram. We write hist, short for histogram. By the way, a rule on Stata abbreviation is that you can abbreviate a command or a variable, most commands and most variables anyways, up until the point where it is still distinct. So because there are no other commands that start with HIST, we can write hist in place of histogram. And we're going to produce really simple graphics here. You'll see later on, and I'll probably put this in a different video, that I do have a section on producing publication quality graphics. But I'm going to keep things simple here because I want to focus on the analysis first. By the way, I'm going to change my scheme actually so that this matches Stata's default scheme. I use other schemes because I'm not a big fan of Stata's default scheme, but I want to show that you can get results that look almost identical to mine. So we'll change the scheme here to Stata's default, which is S2 color, and let's pull up this histogram. And you can see that we get a pretty reasonable picture of the distribution here. The discrete option, by the way, tells Stata that we have a discrete variable, or in other words, one that takes on a finite or countably infinite number of possible values. Countably infinite means basically that there is a level of measurement effectively beyond which the variable can't be further measured. That's a very sociological way of trying to explain that mathematical concept. So basically what that means is, potentially any value could be observed, like let's say world GDP. Who's to say what the limit on world GDP is, right? We could have a massive inflation in, whatever monetary system it's measured in. But we would say that GDP, generally speaking, for let's say using the dollar, for instance, is countably infinite because we generally don't record basically monetary income, especially on the GDP level, certainly not recording it even to anything more precise than $1,000, if that. But even for personal income, unless you're a financial institution and you're keeping track of income in terms of like quarters of cents and things like that, most people, the cent is the smallest unit they care about. So that makes that a discrete variable because that means it's countably infinite. In other words, one way to think about it is, and this is a common line, so I can't take credit for this or anything, but if someone tells you for such a discrete variable how much of it they have, like how much your income is, you can always tell them if you increase by basically if you have any increase in your income, I know what what your new income will be basically. That's not true of things like height, for instance, where if I say your height's going to increase in the next year, if let's say you're still growing, I don't necessarily know by what unit. On some level, I do, because there are limits to how precisely we can measure height at this point in the development of microscope technology. But that's a sort of artificial limit, and it's always changing too. So things like height, where in theory, the more precise the measuring instrument, the more precise the variable itself, we would consider the true variable, like the abstract concept of one's height, to be a continuous variable. So just a brief discussion there that I think is pretty relevant. Education, I would say, is certainly, if we're thinking about years of education, is discrete. So we want to add this discrete option here. And basically what that tells Stata to do is, I'm noticing a typo here. What it tells Stata to do is use as the size of bins the units that the variable comes in, which basically what this does then is turn this histogram into effectively an estimate of the probability mass function, which I've emphasized by also adding the percent option here. So we don't have density on the y, we have percent. And the point of that is that now we're kind of looking at a graph that we actually don't even need these bars really, because we're focusing mostly on the heights actually. So we could eliminate these bars and just have dots here or something to that effect, maybe little slashes. And we would be able to say, okay, so the probability of someone, for instance, here, this is obviously 12 years of education, was around 26 or 7. And I'll show later on how to get more precise y-ticks, just really briefly, because sometimes it's not even about publication quality, it's just about readability. Generally, you can modify those labels by adding things such as like X label, and then you want to put in the minimum, let's say 0. You want to put in the units, let's say 20 might be a little bit misleading, so let's say 2, or 21 we would have if we did 1, so let's do 2, and then we want to put the max, reissue the command, and then we can see this is more readable. We could do the same thing for y too. So we'll go ahead and eliminate that because it's not strictly necessary, but now we can see that this is a nice graph. It tells us basically what we want. And there's no real need to use density or to make this actually approximate a density curve here, because it is a pretty discrete variable. I will show that later on just because I think it's useful to see density, but we're not going to look at that right now. Now we'll do the same thing for father's education. And the main thing to note is that with father's education, we're going to see a lot more missing values here, which makes sense, right? Many people may not know their fathers. They may not know information about them if that person is no longer with us here in the realm of the living, or that person might not know their own education, right? They may not have had a lot of formal education. Definitely, and I actually won't get to this in this video, but if we go ahead and look at, we can actually just do this relatively quickly. If we look at something like father's education, we should do a cross tab here actually. So let's not use education directly, let's use degree. So if we tab, let's say degree, And then I can't remember father's degree. Is it pa degree? Yeah. So here, and let's blow this up a little bit bigger. So if we look at basically who's missing data on degree, we look at the respondent, we see, okay, people that had a less than high school education, looks like 14 plus 23 plus a small share there. So, and these probably sum to 1. So basically, you know, like 38% of people who had a less than high school education didn't report their father's highest degree, but that drops to effectively like 14 and change here if you have a graduate degree yourself. So there's clearly a class bias in who doesn't report their father's degree. So just something to be aware of. Not something that we really deal with in this video, but you want to be cognizant of that. We can run the same basic statistics here. I won't walk through the logic of these in detail. So we first have father's education. We see, you know, predictably enough that, for instance, we had a cumulative share of people that had 12th grade education or less. That was 64.26. And you can see if we come back up here to respondent, so there's a lot of output. At that point, that was only 40.9. So people's fathers had less education than them. That's not too surprising. We can also pull up detailed summary statistics, and you can see here that we get the mean, which is significantly smaller, the median, which is also significantly smaller. And again, we have a slight leftward skew. Standard deviation is larger, so there's more spread. And the percentiles, I didn't actually note which those were specifically, but to make a point-by-point comparison of percentiles, we can just pull up respondent again. And so we see, okay, the 25th percentile for people who are answering the question who are of different ages, right? So this is not a strict kind of generational analysis, because there's people in the GSS who are, you know, currently 80 years old, something like that. But in general, the mean age of respondents versus the mean age of their fathers would certainly be smaller, almost just by definition, really. Here, if we look at the third quartile here, this is only 10th grade education. So 25% of people, people's fathers weren't finishing high school, whereas, you know, you had to significantly like lower than that for people that were answering this survey. So you can also see this plotted too. I don't want to get too far ahead of us, but since we've been referring to the cumulative distribution function quite a bit, this is actually not a default command that ships with Stata, but you can use the command SSC for statistical software components. I think it's an archive where a lot of user-written Stata commands are stored. Install and then CDF plot. That will pull up the cumulative distribution function plot, and we can actually plot. For instance, let's just do father's education. And you can see that we get basically in graphical form, you can see there's a huge jump here right at 12. So basically what this indicates is that there was pretty strong social pressure to get at least that level of education. But then it kind of more slowly increases here. So very, very fast increase right here. Not strictly necessary. It's not that standard to publish these types of graphs in social scientific reviews, but I like to look at them in part because thinking of probability density functions, which can sometimes be difficult to interpret as quite literally graphs the derivative or the instantaneous rate of change of the cumulative distribution function, is often very useful. I won't go too deep into that here, but even if you're not a member of my class and you're interested in learning a little bit about that, I'll link to the slides where I develop that connection at some length, and you can try to get a handle on it that way. So we can also pull up a histogram for father's education as well. I'm just sort of showing that all these techniques work, and you would want to, in a really any type of analysis, show both of these things. And you can also combine these too, by the way. I didn't put that in the notes here, so let's say if we wanted to combine the two graphs, we could write, and then here we're going to need to name these, names for them. Let's say histogram, so this is clear. And here we'll just change this to a Duke, name R Duke, name Pa Duke. And we'll go ahead and run these. And then we can write graph combine. Let's put father first. And again, I won't go into too much detail about this here because I will put a separate video up about that, but I just thought the simple combination here might be kind of useful. So we can put these on the same graph just for the sake of comparison. It's not really about presentation. Again, it's more about, in this case, just ease of analysis. So let's move on to some more advanced graphical techniques. So first I'm going to show you an estimate of that probability density function for each variable. Now, again, we already established that education is very likely a discrete variable if you really think about it, because in theory, while it's time, right, and you could measure time in smaller and smaller increments, at a certain point, most people would say that that's really not relevant, again, as opposed to something like height or weight, where it depends on the scale of the problem. And on some level, you could say, yes, I may not care about it, but this is a real difference in weights. Whereas on some level with education, we might say there is no perceptible difference for any possible purpose between this and that amount of education. And especially if you think about it as years of education, where you're sort of intrinsically saying that the lowest level I care about is complete years. Or completed years of education might be even better than it basically is. You're saying it's the discrete variable. But it can still be useful to look at the density curve. So let's do that. And what this does is basically plot a smooth histogram effectively. So this still works on the same logic as a histogram in a sense, except it's the case that histograms in Stata, which are constrained to have, unless you install a special command, basically the same width, that once you fix that width, then it's really not the area under the curve that matters, it's really the height. And so default histograms in Stata are basically probability mass functions, effectively, even if they say density on the Y, it's still the case that because you're fixing that width of the bars, you don't have to. You can install a command called expra histogram. So you could do this. Just show this really quickly for education. Oh, and it's actually, we've got tied quantiles here. Okay, so let's do that with, let's try, yeah, that's a bit of a doozy. So we'll try this with age. And you can see we can vary the width a little bit. And this is now looking a little bit more like density. This gets a little bit grouchy when you have what are called tied quantiles. In other words, there's some quantiles that basically correspond to the same cut point, the same actual value. Okay, so anyways, coming back to the main idea here. So you can have histograms like this, but Stata is actually basically saying in the case of education that this is pretty discrete. If you have tied quantiles, at a minimum in the data you have are fairly discrete, and data are always discrete relative to the variable, but truly continuous variables tend to have relatively non-sparse or non-discrete data, non-clustered data. But anyways, coming back to the main point. So we wanted to look at this density graph here. And this does work a lot like a histogram, but it produces a smoother graph because it does a couple of things differently. So one, if we have a default histogram and we don't have the discrete option in, let me show one more time an example of that. Keep changing between graphs here. In this case, you can see Stata is actually using smaller increments of the histogram than exists, right? So you can see there's more kind of slots here on the x-axis, and they're actually values of education. Or if we do something different, let's say we do years on the job. Whoops. You can see we've got 31 bins here, but there's actually up to 60 values. There's some binning of the data here. What that binning is Stata or any software, or even if you just do it by hand, is basically taking observations that are within a certain band of values, putting them in the same bucket, like this might be 0 to 2, and then graphing the height of that bucket there. And what that does is it's a nice technique when you do have a variable you believe to be continuous. And you're basically saying, well, if I actually just use the histogram, like I use the discrete values of the variable as observed in the data as my buckets, I'm going to have really sparse, basically really sparse histograms. And the reason for that is that you're going to see all kinds of values that are very slightly different from one another. I can show a really brief example here. Oops. Let's see, do I have the CPS in my data folder? Huh, I actually don't. I have one that would work though. So let's use the NHANES. What do I call it? NHANES merged. Yeah. So let's use it as an example here. Let's say we'll use, oh, how about someone's standing height? And you can see this actually doesn't look that terrible, but we do have some really odd things here. Like there's a little gap here, and we also have this kind of like very sort of spiky structure that very likely is resulting from some kind of rounding error, I would guess. But this isn't really that bad looking at all in a way, but we would want to sort of do away with this because it really doesn't match how the actual PDF we would assume in reality works. So doing something like kernel density for this BMX height is going to smooth that out. And see, this is nice and smooth now. And this presumably looks much more like the distribution function. It's got this weird shape because this merges children and adults, which is not a good sort of, I don't know, I guess, medical research practice for the most part. But if we just restrict it to adults, it would look nice and neat. So let's come back to the GSS briefly. And incidentally, if we want to rerun all the analysis that we've done, we can just do that here. We actually don't need to do all that, but if we did need to, you could just come back and rerun it. So the point about a kernel density plot is that what it does is, instead of like a histogram binning people together, and binning, by the way, is a good thing because we would get rid of that spikiness by assuming that, like, oh, there's only one data point right at this X value, but I'm assuming that if I saw the whole distribution of like the true population distribution, probably there would be more people right next to them. Or I would just think it's a smooth curve, like there's a well-defined function, and it's truly a smooth curve. It's just a population parameter. Anyways, that's what histograms do when they bin, is they sort of simulate that, unless you use discrete histograms. But one thing you can do that's even a little bit better is this kernel density estimate. And what that does is very much like a moving average. It allows different points, different observations to be put into multiple bins, just in the same way that if you have a moving average of, say, someone's weight over time, the weight recorded on one day might show up in, this 5-day band, that 5-day band, and so on, until it's passed out of the window. So that's basically what's happening here, is the height at any one point sort of reflects a moving window. And it also is weighted. It's like an observation is weighted by how far it is from the center of the window. Anyways, it produces this nice estimate. If we did want to think about education as maybe being possibly continuous, of what that distribution function might look like. So that's a little bit about kernel density estimation. You can do the same thing for fathers. And we see here, this looks a lot like the histogram. You can toggle a lot of these settings, by the way. You can change the kernel. This is the Yapanichnikov kind of default, basically, but there's many ways of setting the kernel. But we don't have to worry about that too much, since we're just sort of showing the basics here. You might even want to combine these, by the way. And wanted to make a couple of points here that are relevant. One, this is not a bivariate analysis, because We're not showing a relationship directly between individuals and their scores on these two variables. We're showing basically the two variables as separate. So even though this is in some ways kind of useful, it's not a true analysis of the relationship between two variables. Nevertheless, we can show it. And note here that some commands can't take multiple variables as arguments. K-density is one of them. But many graphs can just be combined with this command 2a and the two graphs. So we'll show this here. And you can see this plots them on each other. This looks kind of nice. You can toggle this in different ways. Again, I'll get to the kind of advanced graphical material later. You might want to move this legend around, for instance. You might want to give these more informative names, but this at least gets you the basics so you can use this in an analysis. So one last thing here is that you can actually combine these plots with histograms and get some nice graphs. I'll just run both of these here because we don't need to look too much at the difference. And you can see we get both of these things on the same graph. It's kind of nice. So the histogram and the kernel density estimate. Now let's look at some other graphical measures of the individual distributions. We're going to focus on box plots here. And the nice thing about box plots is that they actually mark directly different quantiles of the data, as well as outliers by the conventional rule, which is the 2-key rule on a graph, different to histograms, which don't. Now, a histogram, you can generally take a decent guess at the median because it's the equal areas point. And you can generally take a pretty decent guess at the mean as it's the balance point. Although again, like it, doesn't directly mark these things. But what a box plot does that's nice is it actually goes ahead and marks them. So for instance, here we've got the first quartile, the second quartile, or the median, and then the third quartile. And these whiskers come from basically taking the third quartile. Well, let's use this one actually, because I'll explain this in a moment. They start from the first quartile here, then we multiply the IQR, or the size of the box, Q3 minus Q1, the middle 50% of the data. We multiply that by 1.5 and subtract it off from Q1. So that's what this lower whisker is here. And then we mark points outside of that as basically outliers. And these are often called the whiskers here, right here. These are also sometimes called outside values. So one caveat about that that's worth noting, Stata and other pieces of software won't mark whiskers if they, like if 1.5 times the IQR, say plus Q3 in this case, there's no actual data that was that large. So it'll truncate the whisker at basically the largest observed value. So that's just one thing worth noting. So box plots are nice because they actually go ahead and directly mark that information. This rule for outliers, by the way, the 2-key rule is arbitrary. You could select a different rule for looking for outliers, but it's one that's in common use. In general, though, you don't want to drop outliers unless you can come up with a plausible reason for doing so. That means that they are either mistakes or not really part of your population, but you don't want to drop them just because they're large or small. So you can also go ahead and put these two things in the same plot. And one thing I should have mentioned before when I was discussing density curves is that you want to be careful doing this unless these two things are measured on the same scale. So you can do it in this case because we've got years of education in both cases. But in other cases, it wouldn't be that meaningful. For instance, if we tried something like, let's say, and then what's something else that's measured in different units. Yeah, let's say, we'll try, sorry, this one here. So days of poor physical health. These are both numbers, but these are years here and days here. So this is really not very meaningful. Now, what you could do is standardize these if you wanted and take a look at the distribution. So neither of these appears to have exactly a normal distribution, but it still might be helpful to just think about, say, the distribution of their z-scores. So just a brief digression here, but to do that, you can use, actually, no, I won't say that here. I want to discuss the concept of return values in Stata, but I'll leave that until the graphical analysis kind of like extended cut as planned. So for now, I would just say don't put things in the same graph unless they have the same scale. I did want to note that you can also put these horizontally, and you can do this with a lot of different plots, which might be easier to look at. I think it is in this case, and this makes the connection between this and a histogram or a density curve a little more direct. So one thing that's worth noting is that basically this is showing a lot of the same information as a histogram or a density curve. One thing it does show directly is it marks these points, so it makes it easier to see, which is nice. But it doesn't actually show like the relative frequency of values here and here. So we know that 25% of the data are to the left of this, 50 to the left of this, 75 to the left of this. But it doesn't give us that much more information, right? I mean, we see that it's fairly symmetric because the median isn't that much closer to the mean or to Q1 or Q3. But we still don't see like, does this look sort of like this? Are there a couple of different peaks like this and so on? And density curves show us that. What density curves didn't show us was the actual numbers. So what if we just combine the two, which might be kind of nice? So here we're going to install a command again, and I went over that before. If you already have it installed, by the way, this won't do any harm. So just a word to the wise. So let's go ahead and do that here. And again, you can see that the graph looks a little messy. I'll talk about how to deal with that later on. You can also use point and click editing, by the way. I encourage you to put it into code. It really will save you trouble down the road. But if you need to use point and click, you can just come here and click like this and say, change the title. So something like example like that. And then you could change these guys here. But I, again, recommend doing it with code. But anyways, the point was that you can see the Vio plot here, which is really nice. So we see the box, the whiskers, which don't have the whisker anymore, but they mean the same thing. Outliers here don't have any special marking. They're just shown as basically areas under the curve. And we also get the more detailed information here. So for instance, we see, as I mentioned before, that like within the middle 50% of the data here, we do have different looking shapes. So this shape here looks fairly different to this shape here. So it's useful to combine both of these things. One note is that these take a long time for Stata to draw. So careful using these with data that have tons of observations. Generally speaking, we don't need to save our graphs. Again, that's the point of writing it here in the code. And when you export things in Stata, I'm generally a stickler for doing things the right way. But there's really not too much reason not to simply take a screenshot of a graph once you've fixed it up nicely. So that's a way to export stuff. You can also save it directly, but you don't necessarily need to. So we won't do that. And so that basically concludes the univariate analysis. We've kind of seen how to plot these quantitative variables. So let's move on to the bivariate analysis. And this will go relatively quickly, actually. So we'll start with just a simple graphical analysis. So we'll put up a scatter plot. And I want to just note two things here. We pull up the scatter plot. The first is that the y variable comes first in the scatter syntax in Stata. So we say scatter educ because that's the outcome, and then pa educ. And the second is that we use this jitter here, jitter open parenthesis 5 close parenthesis, to tell Stata to produce 5% random noise on the graph. And the reason we do that is that otherwise this graph would appear a little bit dotty. And what I mean by that is it would look like this. And you can see here, there's clearly a pattern, but it's a little bit harder to suss out the pattern because there's all this down here, right? And if we had data down here, it would be really impossible, even though if we just had a few points down here, it actually wouldn't change the basic pattern too much. So the reason for this is that these data are pretty discrete. And so what that means is that we have lots of people that have the exact same combination of values. And so Stata is just stacking them on top of each other effectively, except this is not a three-dimensional plot. So if we did have a three-dimensional plot, which Stata actually, has a hard time with what are called joint density plots. So you can produce those things in Python, for instance, and I think R. But we can't really do it in Stata. So there's a couple of ways around it. One of them is to use a jitter, which produces that random noise. And you can see here that now it will make more of that noise where there's more observations. So it draws out the pattern. We can see like, oh yeah, there's not actually that many people out here. There were tons of people clustered around here. There's other ways too. So you could use a contour plot, which basically uses topographical mapping techniques of using basically concentric circles and other sort of kind of elliptical shapes to simulate basically a contour plot, like an actual contour plot, which shows the, again, topographical layout of a place. So here, I went ahead and set the levels to 10, so possibly up to 10 concentric circles. And what this is showing us is it's as if we had a mountain here, and the two peaks of the mountain are right here, which again tracks with kind of what we saw before. Lots of people with fathers have 12 years of education, and so do they. And then secondarily, a pretty common outcome is 12 or thereabout for dad, and then around 16 for them. And then pairs of graduates here, a little less common. And then not as much data down here, over here, over here, or up here at the upper ends. So that's another way to show that density without relying on a scatter plot that might not be very informative. So those are cool, but it's kind of hard to add regression lines to them. So let's go ahead and add a regression line. And you can draw scatter plots with regression lines in a couple of ways. One is to use that same generic syntax we learned before. So two-way, and then we'll write two graph commands, and then Stata will put these on top of each other. So first we'll just run the scatterplot command, then we'll write lfit for linear fit, and then y variable, x variable. So let's run that now. And you can see here that this is the result that we get. So this looks relatively nice, good basic analysis. Again, we'll talk later on about maybe getting rid of this legend if it's not very useful, maybe giving this line a little bit of dashedness so it's easier to see, but this gives us the basic picture. So not too bad. And we don't really have too much more to say about the regression line here until we get to the numeric analysis. So for now, we can just know it minimizes the sum of squared deviations basically from that line. That's what the technique does. So the line is the line of best fit by that convention. And it gives us a sense of what the linear relationship between the two things is. It doesn't capture nonlinear relationships very well, which I've shown in my lectures. But we don't really need to worry about that too much until you encounter such data. So let's move on to the numeric analysis. So first we'll begin with the correlation. So we'll write core aduk pa aduk, and then we're going to come back here actually to the command window again. And you can see that the correlation is 0.4129. That's relatively high in a situation where it's rare to get really strong correlations in a sociological setting because there's all kinds of influences on these different variables. You can think about the correlation coefficient in many different ways. You could think about it, for instance, as the effectively the mean of the summed z products of the two variables. If you think about the two variables as vectors in n-dimensional space, it's the cosine of the angle between them, using the law of cosine to derive that. So it's basically a measure of kind of how angularly close the two vectors are in that sense. Or in other words, basically, all the deviation products over the total variation in X and the total variation in Y. Although remember that X and Y really aren't that meaningful here because it's a totally symmetric relationship. So before we do regression, we're just talking about correlation, and correlation, there is no sense in which there's really an X and a Y variable. And we can also say, for instance, that because this varies between -1 and 1 inclusive, it's strong or weak is kind of subjective, but we can get a sense that okay, it's not minuscule, but it's not giant, right? It's not like these two things are truly super closely related. Again, that's kind of rare in sociology or social sciences generally. And we know that it's positive because there's not a negative sign there. Okay, so we can also get the R squared, which is jumping ahead a little bit, but it's easiest to tackle this now before we look at regression. And there's a couple of ways to do this. One, we could just copy paste. So we could copy this and we could write display, or DI for short, but I'll spell it out the first time. That number, then caret key, then 2. And that gives us the R squared. There is a better way to do it from a programming standpoint, which is to use what are called return values. Return values from any command are the things that are stored in Stata's working memory, so to speak. They're the things that Stata is keeping track of that it won't keep track of after you run other commands, because otherwise your computer's memory would blow up, basically. But it will keep track of it temporarily, and we can use that fact, and Stata is built so that you can use that fact to, for instance, not need to copy paste or not need to round. So you can actually find out what return values exist for a command by writing help in the command. So let's look at it for correlation. And we see the help file here, but we're going to scroll down all the way to the end, which is where these are stored. And you see the stored results here. And so, for instance, we get the number of observations. So we could say, how many observations were there? Actually, it's spelled out right here, but let's just try this. So we'll rerun this. Notice that it has to be the most recent command or else this won't work. And we get 1687 right back. But we could also have it give us the correlation coefficient. So we could write display R row, which is the Greek letter that actually looks a little bit like a lowercase p, but it's actually the population correlation symbol. And we see that we get the value here. And notice, one, there's less rounding. And two, you can remember what conceptually this is. So instead of having a do file that's junked up with a bunch of like specific numbers, which you may not remember why that number is in there, it may not be obvious to someone why that number is in your do file. You can instead write R row to mean the results of that correlation. And the result in this case, like give me the actual correlation coefficient, the Pearson correlation coefficient, if we want to be really precise. And that's a little bit nicer because it just looks more elegant and it reminds you of why you did that. So we can say display R for return row and then squared. And this gives the same value that we saw before, but one, it's a little bit more precise. And two, it's just also more elegant to look at. So how do we interpret this? We interpret this as saying about 17%, pardon me, the variation in our outcome variable is explained by variation in our predictor. And notably, that'll be true no matter which is outcome and which is predictor. But in this case, we're thinking about education as the outcome. And then what we want to do is go ahead and look at the actual regression output. So here, I'm going to actually use the option no head for no header. And I'm going to do that because I don't actually want us to look at all the regression output right away because it's a little bit complicated. I will show what that is in just a moment. But this gives you the basic output. I know this still might seem like a whole lot of things: standard error, t-statistic, p-value, and the confidence intervals for the kind of standard 95% confidence. We'll get to all of those things in SOAS 360. And if you continue on your stats journey, I hope that you get to learn those things because they're not too complicated. All of these things should be covered in any good basic stats class. But for now, we're just going to focus on the coefficients. And we'll focus here primarily on the coefficient on the variable itself. So how do we interpret this coefficient? Well, we say that for a unit change in father's education, we expect to see a 0.29 increase in respondent's education in the units of that variable. In other words, when father's education goes up by 1, we expect the respondent's education to go up by about 1/3 of a year. And this is jumping the gun a little bit, but this very large t-statistic and small p-value means that these results are statistically significant. And for now, you can just know, if you're curious about what this confidence interval means, this gives a plausible range of values for the true population parameter. And that basically comes from the standard error and the normal distribution, or a close to normal distribution called the t. Again, more on that later. You can also interpret the coefficient. In this case, it's not totally meaningless on the constant. And you might wonder, why is there a coefficient on a constant? That doesn't really make sense. It's actually because the constant, if you write this out using linear algebra, is a scalar that you multiply a vector of ones by. So technically it's a coefficient, which is why it's in this column, although that is initially confusing. It was to me the first time I saw Stata, but didn't know very much linear algebra. So this says that if you have 0 years of education, or your father did, pardon me, you're predicted to have about 10 2/3 years. Not always meaningful to interpret the constant. In this case it is, but actually there's more of mathematical reason for selecting a constant than usually there is a substantive reason. So that's how we would interpret that. Not too tricky. We can also look at the full regression output, and I'll show you kind of what that's about. Also, I guess just one brief comment I wanted to remind people of. So this video is not a full course in basic descriptive statistics of correlation and regression, but it is worth remembering that in the bivariate setting, the regression slope is the correlation coefficient R multiplied by the ratio of standard deviations, standard deviation of the Y to the standard deviation of X. And we could actually demonstrate that really quickly. So let's pull this up here. Right, and then we can actually briefly, I won't totally explain this part yet, but I'll just show you quickly. We'll write sum adduc. We'll store in a scalar. We'll call this sy here. This is the outcome, equals, and then we'll write rsd for return standard deviation. And then we'll write sum adduc. And this is just to get the return values in Stata's memory. And we'll say scalar sx for predictor equals rsd, but now it's the standard deviation. And what we can do is say display, let's actually get the correlation up really quickly. So adduc, adduc, and we'll do a scalar here. So ed r equals r rho. And we'll tell Stata to multiply, so ed r by sy divided by sx. And you can see that this actually gives us that same regression slope from up here with a little bit of error. But the reason for that is actually that in this case, we have way more people in the education group. So we didn't restrict it to only people who are had values on father's education. So this is not actually the subset of people here who are included in the analysis, because the limiting factor, so to speak, is people that have values on this variable. So it would be more exact if I had remembered to write something like sum adduc if not missing adduc. We can actually, let's just show this for the sake of exactness. So we'll replace that old scalar with a new one. We can actually rerun the command here. And you can see now this matches even more exactly the coefficient from up here. So that's how we solve that little gap. So what this is really doing is saying, take the most abstract form of the relationship between the two things, and then basically you want to have X inputs. So let's say, okay, we're multiplying by X in the end. So I want to basically standardize a unit change in X. So instead of seeing it as just a general change, I want to see what standard deviation changes it. And then because now we sort of have that standardized change in X, we want to multiply by a standardized change in Y, or by its standard deviation, to get a concrete output. You can also think about this in a whole variety of different ways. For instance, as I will discuss in class later in the coming week, you can think about this as showing you why it's called regression, because the correlation coefficient is usually less than 1. So what that means is standard deviation change in X results in a less than 1 standard deviation change in Y, hence Y regresses to the mean. It's actually the origin of the term. Coined, I believe, by Galton, who's sort of an unfortunate figure. Unfortunate in that he was a jerk. You can also think about it just in terms of the method of moments solution to the normal equation. So you can write out some conditions that you want to be true of your sample, such as, for instance, that the residual term, you believe that the error term and the predictor are uncorrelated in the population. So you force the sample estimate of the error, which is called the residual, to have 0 correlation with the predictor. So you basically orthogonally project the outcome onto the vector space of the predictor, and basically the component that works like the short leg of a right triangle, that is if your prediction is good, is the residual term. So there's all kinds of different ways to think about this. But anyways, that's the point, that's sort of where this comes from, and that's how we interpret it. So let's look at that full output again. So actually, we'll eventually learn what almost all of this stuff means, or have some sense of what all of it means. But I just wanted to show briefly that you can also think about the correlation coefficient squared, which is a pretty good measure of the amount of variation, or it's a good measure of fit. And what it tells us directly is that it gives the share of variation in the predictor that is, share of variation in the outcome explained by the variation in the predictor. But you can also see here too, that the model sum of squares right here over the total sum of squares, or in other words, basically the variation in the y-hats, the predictions, over the total sum of squares, or the variation in the outcome, also that will actually give us the same thing as r squared, because it's the same exact measure of fit, actually, which is a really interesting fact, kind of a cool fact. So let's come here, and you'll notice that we can again use return values to show this. And interestingly, even though we don't have the total sum of squares in the outputs or in the return values, we can actually just use the fact that the model sum of squares and residual sum of squares sum to the total sum of squares to get this quickly. And we can see that the model sum of squares, or the model sum plus the total, or the residual sum, pardon me, gives the same thing basically as r squared here. So those effectively come to the same measure. And now we can finally turn and look briefly at the analysis of the residuals. So let's come here. And what this is going to show is a plot of the residuals against the predictor. Now, notably, there's no linear pattern here, because by construction, as mentioned before, we actually force the residuals to have zero relationship in a linear sense with the predictor. That's actually how we come up with those sample estimates, or it's at least one way of deriving the sample formulae for the OLS estimates. But you can see other patterns here, such as nonlinearities. Here we don't have really strong nonlinearities, but we've got a fairly different spread of the residuals here as opposed to here. So the spread gets pretty tight when dad has a high degree of education. You know, it kind of starts around here. So it seems like there's a bit of a ratchet effect. So it's not like once fathers reach a certain level of education, they're generally pushing their kids to have similar levels of education to them. And that's not as much the case with fathers that have lower degrees of education. Although this is actually the fitted values are predicted. So this is really more about not necessarily father's education, but scalar multiples thereof, but the point comes to the same thing. What we see here is that the spread of the residuals is different at different points, which is a condition called heteroscedasticity. In other words, the conditional spread of the points on values of the predictor is different, meaning that the fit of the line is not that good in some places and it's better in other places. And we can actually see that again by just pulling that up one more time. And you can see this is going to look very much, oh, I should put the jitter on. That will perhaps bring the pattern out a little more clearly. And you can see here that the spread is noticeably a little bit less tight around here than it is around here. So what that means is that we're probably leaving out some relevant variables. So for instance, the fact that there's been more of a push over time to get people through a certain degree of formal education, regardless of how much their father had, means that even though it's not the case, we don't live in a strongly egalitarian society, you know, it's not like the public school system is getting everyone through college and grad school or something, but it is the case that even people whose fathers might have relatively little education, between parents generally striving for their kids to have better lives than they did, and through the fact that it's, you know, effectively illegal in certain places to not actually get yourself through a 12th grade education, you can be charged with truancy and this sort of thing, which is not a law, obviously, that's been around for the entirety of American history or been enforced to equal degrees in equal places, that means that there's probably some other influences, such as when someone was born. So for instance, I won't comment too much on the results of a multiple regression, but we could say regress education on father's education, and then we could do either the year someone was born or their age. It's going to come to the same thing. Let's use cohort just because that's conceptually a little closer. And we can see the R squared, increases somewhat, not too much, but it appears that this is actually a relevant predictor anyways. And so maybe something like that explains it, explains some of the reason that the spread was, a little bit messier. And we can actually pull that up and see. So does adding in our predictor, our second predictor, which we don't have time to talk about multiple regression in this course, unfortunately, beyond just saying that it's possible, and this is what it looks like, we can actually see that the heteroscedasticity appears to be getting a little bit less severe here, possibly indicating that this is a relevant predictor to include, besides the fact that it's statistically significant. So yeah, that basically shows us how we could do a simple bivariate analysis with plenty of commentary on some other relevant topics in Stata. And I would recommend, as a practical matter, before I discuss publication quality graphics, I would recommend, generally speaking, including in any report, especially one for one of my classes, the following information. I would include the correlation coefficient and its square and an interpretation thereof. I would include the regression equation. So for instance, we would say in this particular case, let's use the bivariate situation here. Something like the estimated regression equation is y equal to 0.29x. And you should probably write out pa educ or father's education plus 10.67. Rounding is fine. I would just try to round consistently. And I would also include information about, say, the standard deviation and the mean of each individual variable. And I would include probably a box plot of each variable, a histogram of each variable, and the scatter plot with the jitter and the line of best fit. You should make sure that your graphs are always labeled nicely. So we haven't been doing that here, period. We have been doing 0 of that just because I've been trying to show you basically how to get the graphs up, what the commands are. And I'll go into quite a bit of detail about how to actually give these things nice titles in the following video, which will apply to really any analysis, not just quantitative variables. But that is something that you should certainly be aware of. So I would never hand in, even for a simple school project, something as simple as this, even if you remember the jitter, which is kind of important. I would never hand in something like this without even a title. So you'll see that you can add a title in a couple of ways. Again, just to show this briefly, you can really quickly add one just by pointing and clicking, trying something like, let's say this here. You can, so text, you can put a title in here too, but it's also very easy to do with code, which I would generally recommend. Again, more on that to come, but this is the basic idea. So we would just say title here, and just to show that this also is a way to add text, we can put it in like that. So usually the options are pretty intuitive here. Thanks for watching, everybody. I hope this is helpful to you, and stay tuned for more information, a little bit more about Stata and publication quality graphics, as well as other types of analysis. Thanks for watching.
So I wanted to add a brief addendum on outliers here. And I wanted to do that even though we already discussed outliers before in the context of box plots, because really 2 reasons. One, even though you should be very careful about dropping outliers because because outliers are outliers according to the 2-key rule, which is only one of many, doesn't necessarily mean that there's anything wrong with those data points. So it's oftentimes useful to, instead of just relying on the box plot, actually, even if you want to just rely on the box plot, you need to know what numeric values exactly are associated with being outliers. So I wanted to show you how you can use a little bit of advanced data coding that I've already alluded to in this video to actually create a variable that encodes which items are outliers, or possibly just to come up with a variable that only has non-outlier variables on it, or observations. And also because in the course of creating this new variable, I thought it would be an opportune moment to show you a common Stata gotcha. So even though in this video series, I'll focus more on creating new variables when I discuss qualitative variables, it is still sometimes relevant to create new variables in the case of quantitative variables. And so there's a very common gotcha that has to do with missing values that I wanted to make sure everyone is apprised of. So let's start by discussing outliers. So we know that the box plot, which Stata produces and which most software produce by default, creates outer values, basically, as they're sometimes known, that is values beyond the whiskers. And why don't we just pull up the box plot again so we know what we have, what we're referring to here. So when we pull up a box plot, for instance, and you can see I'm recording this part of the video a little bit later, so I need to change my scheme back to the stated default at some point here, although I guess it's not strictly necessary. But you can see we've got these outside values here, and these are considered outliers according to the 2-key rule, because these whiskers here represent basically Q1 and Q3 minus and plus 1.5 times the IQR or interquartile range, which represents the middle 50% of data, or rather the cut points that enclose the middle 50% of the data. So that is ultimately a rule that could be otherwise. It's somewhat arbitrary. So if you really wanted to consider dropping outliers, you would want to first figure out, well, what are the actual values of the whiskers, so that I can figure out basically whether or not these are implausible by some kind of other criterion. And I've already discussed earlier in the video the reason that these whiskers in this case don't extend quite as far out as, for instance, this whisker does. It has to do with the fact that Stata will truncate the whiskers to the highest and lowest observed values if those values are less than what the whiskers would otherwise be according to the 2-key rule. So in this case, we can just kind of eyeball it and say, okay, well, it appears that in this case, the value here is about 6. And I'll show you, you can actually go ahead, let's fix the scheme here, just so this looks like everyone's scheme at home. We can actually tell Stata to tick the axis a little more precisely, and that's easier to do with vertical box plots. So we'll say this, we'll go ahead and write Y label 0, 1 to 20 like this. And what this does is it goes ahead and actually ticks the Y axis from 0 to 20. You can see it gets a little bit messy. We could make that maybe a little nicer looking by putting in 2 here instead of 1, but I just wanted to demonstrate the technique. And that lets us see pretty clearly here that for father, the kind of outlier cutoff point here is 4 years of education. For respondents, it's 6. But we can also pull up that information directly without needing to resort to this, and it's oftentimes useful to have that. So it'll also let me tell you about a couple of useful advanced data techniques. So the first thing we're going to do is actually put into the working memory the summary statistics for education. So we're going to say quietly sum education, comma, D for detail, and quietly tell Stata that it doesn't need to display the output. And that's oftentimes useful because we don't necessarily need to see it again. We just want the results in Stata's effectively what it is like its working memory as a computer. So let's pull that up here. And you can see that quietly sum doesn't pull up anything. And now we're going to, again, use those return values that I discussed before. And remember that these are basically just anything that Stata will temporarily store kind of ready to hand when you run a command. And you can always find out what those things are by going in the help file. So let's see, for instance, for summary statistics, which of those values are available to us right after we run the command. We'll come down to the very bottom, and you can see that these are the values. So things such as the number of observations, the mean, pretty much everything that the command outputs is going to be available in the stored results. So what we're going to do here is actually create what's called a scalar. And a scalar is a term in linear algebra that just means a single number as opposed to a vector or a list of numbers, which can also be understood as the coordinates of basically a point in n-dimensional space. But here, scalar just means basically Stata will store numbers for us under English names or potentially any language that are easier to refer to conceptually than writing down numbers. So what we can do is tell Stata to calculate the lower bound for the 2-key rule for outliers without needing to actually write down all the numbers ourselves, because we can just recall, okay, Stata stores the 25th percentile in its working memory, and it also stores the 75th percentile. So you can see here, we just write down the formula, and basically we're going to say, take the first quartile and subtract out the interquartile range, or the 75th minus the, sorry, that should be 25th value, and then multiply by 1.5. And I need to change this as well. I don't know why I wrote that way, but that's okay. So we'll go ahead and store this in the scalar lower bound ed. And this is just easier to keep track of conceptually than if we actually go and write down all those numbers, in part because if you send this file to someone later on, you might wonder, well, gosh, why did I write down those specific numbers? It might not be obvious to you that you were using a particular formula. The other nice thing is that in loops, for instance, like if I wanted to do this for a whole set of variables, which is possible to do, although a little bit beyond where our course is, then you basically need to come up with this rather than write down the actual numbers. So let's go ahead and do this. And we can display the value by going ahead and writing di and then the scalar. And we can see here that we got 6, which is what we got before when we did this for when we just kind of visually figured that out. Let's do the same thing for the upper bound now. And then we can go ahead and display that. And you can see that we're going to get a number that's larger than 20, which again is the reason that the box plot appeared compressed, because that upper whisker was actually truncated at the value 20 rather than 22. So now what we could do is if we wanted to drop those outliers, which I wouldn't recommend in this case, these are not like true implausible values, they're just unusual values. But if we did want to maybe rerun the analysis without them, there's a whole variety of ways to do that, but a simple way to do it that also brings up some relevant points with respect to Stata programming is we could just make a new variable that returns missing values if people are outliers on that old variable. So here's how we would do that. We would generate a new variable. Gen is short for generate. It just makes a new variable. And we're going to generate it and call it gen educ no OL for outliers. And it'll just be equal to the value of education if education is greater than the lower bound and less than the upper bound. And the if condition basically works like you would expect. If you have any experience with mathematical logic, this will seem really familiar. If not, it just tells Stata to do this only if something is true. So it's very much like human language. And then finally, well, there's actually really not too much more to say than that. Other than that, if this is not true, the result will be that we just have missing values. So we should see here, like, let's summarize Hadoop really quickly. So we have 2,345 observations. At a minimum, to check our work, we should be seeing that this returns fewer people. So, and another way to do it too is that when we look at the minimum and maximum values, they should be basically the values that we got here, or actually smaller and larger than those values respectively. So if we do that, we see that the smallest values here, the 4 smallest for our new variable, are all 7, which tracks because our cutoff was 6. And the upper bound isn't really affected because the upper bound was larger than any observed values. So you can see that we've here dropped the lower bound outliers, didn't change the median, and it only changed the mean slightly, but you still might want to do this depending on the context. And one way you can verify that we've gone ahead and actually replaced people who are outside the bounds is to, again, learn a little bit about the basics of how Stata works. So one thing we can do here is maybe sort people by the value of education, which will list everyone in the data set from whatever current order there is down to basically from lowest to smallest on education. So let me actually show that here. So we can always pull up the matrix of data, AKA the spreadsheet, to get a tactile sense for how Stata looks on the back end here. It's actually not really how it looks in the internal representation of the computer, but it's a way of representing it that you might find familiar and comforting if you're used to Excel. So you can see here we've got all of these different variables, and the sort order very likely is just given by the ID variable. So we can actually scroll over here and see if it appears to be sorted by ID. May or may not be, and it actually doesn't really especially matter. Yeah, so it is currently sorted by the ID variable, but it really doesn't matter. So what we're going to do now is actually sort by the value of education. So we'll do that here. And the reason I'm doing that is that it'll make it easy to pull up people who are outliers and then compare them on the old and new variable. So now what we're going to do is list observations in 1 through 25. Be very careful with the list, by the way, because it'll just list everything if we tell it to do so. So be super careful. If you have a giant data set, you can sometimes get your computer to overheat. You might need to restart. But here I'm just saying list in 1 through 25, and I'm also telling it to only list 2 variables. So we're going to list the value of education and then the value of education, no outliers. And if we do that, we'll see here all of these people would have been considered outliers by the 2-key rule. And so they have a value on education, but no value on education, no outliers. So this is kind of nice here. Now, again, you want to be very careful about doing that. Even just running the analysis without outliers could be misleading. At most, what you might want to do is run the analysis with and without outliers. And I won't show that here because even then, I don't think that's always necessarily that useful if you really do think that these people are drawn from the same population as the people who are part of the main bulk of the data set. There's kind of a maybe a bit of tacit knowledge, if you want to use that phrase, among experienced practitioners of data science that a kind of common amateur mistake is to be too eager to drop outliers, in part because people are, sometimes assume just because it's how box plots are constructed in the standard fashion that, there's just this objective rule for outliers, but it's really not the case that rule has anything other than just kind of a cutoff, meaning go investigate these values further. But there's, unlike the formula for the variance or the mean, for instance, which we fairly rigorously derive in my class, the outlier formula does not have a similar derivation. It's just a kind of offhand heuristic. So I wanted to finally let you know about this Stata gotcha about missing values. So we saw before that missing values are often represented with what's called system missing, or in other words, just a dot. And missing value conventions actually differ pretty significantly across different kinds of software that you might use for statistics. And Stata has its own kind of quirks here. For the most part, this is a nice way to visualize things, in part because, among other things, it's just easy to tell that it means missing. And secondarily, Stata knows to omit missings from the analysis. So if we scroll back up here, we see that education no outliers, we actually do have a smaller number of people included. So this does not include missings. And similarly, if we go ahead and tabulate it, and notice here I'm just abbreviating education no outliers because no other variable starts with this unique string, so we don't have to type the whole thing. You can see that it goes ahead and ignores those missings. We can include the missings if we want by doing this, and you can see they're placed here at the bottom. And that actually brings up the most important point I wanted to mention about missing values, which is why are these missings at the bottom? They originally were very small values, right? At least the majority of them, because before we did this missing variable, or this variable that made more missing values, basically there were only 3 people that had missing values in education, and who knows what they were. But so why are missing values down here at the bottom? Most of these people were originally actually quite small values. And the point is that Stata actually interprets missing values, or it internally represents them as infinitely large values. And that's a good thing in a way, because Stata is smart enough to just go ahead and exclude those from analysis for the most part. And so you don't have to write any special commands to make sure you're avoiding the inclusion of missing values, because Stata will just say, well, I don't know what to do with that. But one problem that arises is that Stata will then basically, sometimes when you write certain kinds of conditional commands, forget to omit them because it doesn't always know to consider these like true missing. Sometimes it just defaults to considering them infinitely large, but you can write statements in Stata. And let me give an example just to make this more concrete, such as count if father's education is greater than 16. That will go ahead and just count everyone who is greater than 16 on father's education, so 17, 18, 19, 20. But it will also clearly count way too many people. So remember that we only had, if we sum father's education one more time, we only have 1,600 people here, but Stata is suddenly saying that half of the fathers in the data set had more than a college education. That's like utterly implausible if you know anything about American society during the period in which most people's fathers, people who were answering the GS in 2018, when their fathers were getting an education, or just from earlier in the video, that's totally implausible. So why are we getting this giant number? Well, what if we just go ahead and tabulate education of the father? And if we just briefly take a quick spot check here, 1965, 1348, we can actually really quickly figure out what that ends up being using Stata's display function, which is a nice reminder here. So we can do this, and we see we get 145, which is obviously far smaller than 806. So what's going on here? Well, basically, we weren't cautious enough about our conditional statement. So What we should have done is go ahead and write count if father's education is greater than 16 and there is a not missing condition for father's education. So the exclamation mark and the tilde both mean not in many programming languages. That said, I generally prefer to use the exclamation mark because the tilde also means approximately equal to in a lot of cases where you can't write the actual kind of curvy equality symbol. So people often write tilde equals, which is super confusing because approximately equal to and not equal to are very much not the same thing. So in general, I just find it easier to use the exclamation mark, but a tilde would work here as well. So let's try this now. And if we do this, we see we get 145, which is actually the number we got here. So by excluding people who were missing on father's education, Stata is smart enough to know in this way of writing it that it shouldn't count people who are missing. But if you just do it this way here, Stata does, in this context, consider people that are missing to be greater than 16. It's a little strange that it's programmed in that way, but it's still smart enough here to go ahead and exclude those people. But it's just something to be aware of. This is one of those gotchas that comes back over and over and over again, because a very large share of the time that you're making new variables, you might want to do something like only list people on this variable as ones if they are millionaires, but you're going to get people who are missing their income variable, their value in the income variable as well, which is going to be entirely inappropriate. So that is a common gotcha that I would like you all to be apprised of. And that's where I'll end the first video in the series on quantitative analysis, and I'll pick up in the next video in the series with the fun topic of producing publication quality graphs. See you later. Thanks for watching.